Have you ever stopped to think about what's really happening deep inside your solar panel? Or, the little LED light in your phone? It turns out there's this hidden microscopic battle going on that decides how bright they shine and how much power they actually produce. Today, we're going to pull back the curtain and find the efficiency thief that's been holding our technology back.
It really is a great question, isn't it? Why can't we just get every last bit of energy from the sun and turn it into electricity? 100% efficient solar panel sounds pretty good, right? And why does some of the energy that's supposed to be making light in an LED just kinda vanish as heat? Well, the answer to all of that lies in this fundamental process that's happening trillions of times a second inside every semiconductor.
Okay, let's dive right in. The efficiency of pretty much any semiconductor device comes down to this constant struggle, like a tug of war happening inside between two opposing forces. If you can get your head around this one conflict, you'll understand why our favorite gadgets work the way they do.
So on one side of the rope, we've got generation. This is the good part. This is where energy, say from sunlight, creates these little mobile charge carriers that can do useful work. But on the other side, pulling against it, is recombination. And that's the process that gets rid of those very same carriers. One creates potential, the other destroys it. And the balance between those two, that's the whole ballgame.
To really get this, we need to meet the stars of our show, the charge carriers themselves. And honestly, the best way to understand how they behave is to imagine them at a party, a very specific, invisible dance party.
The main act here is what's called an electron-hole pair. So picture this. When an electron gets a jolt of energy and moves, it leaves behind this empty spot, which we call a hole. And that hole acts just like a positive charge. So think of the electron as a dancer, and the hole is just the empty space they left on the floor. Now both of them are free to move around and cause some action.
Okay, so let's set the scene for our party. Our dance club has two main levels. Downstairs, you've got the main floor. This is the valence band. It's totally packed with electrons, all paired up, not really moving much. But then above it is the conduction band. Think of it as this exclusive, high-energy balcony where the cool kids hang out. Up there, electrons can move around freely and create an electric current.
So, generation happens when a photon of light, like a flash from a strobe light, hits the dance floor with a ton of energy. It zaps an electron, giving it just enough juice to leap all the way up to that balcony, the conduction band. And voila! This creates our mobile pair. We've got a free electron on the balcony and its abandoned dance spot, the hole, down on the main floor. But that high energy state, it doesn't last forever. The party has to wind down. Eventually, that excited electron up on the balcony is going to lose its energy and fall back down to the main floor to reunite with an empty spot, a hole. And that is recombination. Now, here's the million-dollar question. What happens to all that extra energy when the electron falls? Where does it go? Because this is the absolute crucial point. Not all recombination is the same. There are basically three main ways an electron can get back down to the dance floor, and the path it chooses determines whether we get something useful, like light, or just something wasteful, like heat.
And here they are. First, you have band-to-band, which is the direct, perfect path that gives us light. But then you have our two efficiency thieves. There's Shockley-Reed-Hall, which is like taking a sketchy detour because of defects in the material. And then there's Auger, which is this messy three-person collision. And guess what? Both of those just generate useless heat.
All right, path number one is the hero of our story. It's called band-to-band or radiative recombination. The electron up on the balcony spots a hole directly below it. It makes this clean, perfect leap, and as it falls, it releases all its extra energy as a flash of light, a photon. This is literally how an LED works. It's exactly what we want to happen. It's clean, it's efficient, and it's super productive.
But what if the material isn't perfect? What if the club is a little run down? Well, any defects or impurities in the crystal create these things called trap levels. A good way to think of them is like a rickety hidden staircase that goes between the balcony and the main floor. So instead of a clean leap, the electron takes this inefficient detour, stepping down and releasing its energy not as one big flash of light, but in little puffs of heat through vibrations we call phonons. This is Shockley-Reed-Hall recombination, and it's a huge source of inefficiency.
Now the third path, Auger recombination. This one really only becomes a problem when the club is absolutely packed, when you have a really high density of electrons and holes. In this scenario, an electron tries to fall back down, but instead of releasing a photon, it bumps into another electron on the balcony and just transfers all its energy to it. This shoves that third electron into an even higher, unstable state. It's just a messy, chaotic process that in the end just generates more heat.
So you might be thinking, okay, why don't we just use materials where that good light-producing path is the main one? And that's a great question, which brings us to the undisputed king of all semiconductors, silicon. See, silicon has this very particular problem that makes it a really, really terrible dancer when it comes to making light.
And this slide really nails the issue. It's all about alignment. It's geometry. In what we call a direct bandgap material, the lowest point on the balcony is directly above the highest point on the main floor. Easy peasy. The electron can just drop straight down. But in an indirect bandgap material, like our friend silicon, they're misaligned. In order for the electron to drop down, it not only has to lose energy, it also has to change its momentum. It literally needs a helpful shove from a lattice vibration, a phonon, just to make the leap.
So having this extra requirement, needing both a photon and a phonon at the exact same time, makes that good light-producing recombination in silicon incredibly slow and super unlikely to happen. And because that good path is so hard to take, those efficiency-killing detours, Shockley, Reed, Hall, and Auger, they become the main ways that carriers are lost. And that, right there, is why making silicon LEDs is so darn difficult. And it's why fighting recombination is so critical for making better solar cells.
Okay, so knowing the different paths is one thing, but there's another piece to this puzzle. We also need to know how long our little dancers stay up on the balcony before they fall. This is an absolutely critical parameter, and it's known as the carrier lifetime.
The carrier lifetime is, simply put, the average amount of time an excited electron can exist before it gets eliminated by recombination. You can think of it like a ticking clock, a race against time. The longer the lifetime, the more time that carrier has to do something useful for us, like travel to an electrode and become part of an electrical current. A short lifetime? That means it just recombines and is lost almost instantly.
So how on earth do you measure something that happens so fast? Well, one really common way is a technique called photoconductance decay. Basically, scientists take the semiconductor and hit it with a really quick, intense flash of light. That creates a whole bunch of new electron-hole pairs, which makes the material more conductive for a split second. Then, they just watch how quickly that extra conductivity fades away as the pairs recombine. The speed of that decay tells them exactly what the average carrier lifetime is. Pretty clever.
And this brings us right back to our original question about solar panels. For a solar cell to be efficient, we need that carrier lifetime to be as long as humanly possible. We want the electrons and holes created by sunlight to survive long enough to be gathered up as electric current. Every single carrier that gets lost to that sneaky Shockley-Reed Hall detour or that messy Auger process is a little bit of stolen energy. It's a win for the efficiency thief.
So when you boil it all down, the future of really efficient LEDs and super high-performance solar cells, it all rests on our ability to choreograph this invisible dance. It's all about making purer crystals to get rid of those Shockley-Reed Hall detours and engineering new structures that force electrons to take the good radiative path. It is a constant battle, and it's being fought on an atomic scale. And the next big breakthrough? Well, it just might come from the material that finally, truly masters the dance.